All right, internal, external forces. Not a whole lot of math with this, more of thinking about situations and determining if extra work is being provided or not, okay? So the question is, what does work do? Well, there's two types of forces, internal and external. Now, internal forces are what we call conservative forces. And what that means is that total mechanical energy doesn't change. So potential energy, when these forces are applied, will equal kinetic energy at the start and at the finish. So total mechanical energy doesn't change. Examples of internal forces: the force of gravity, force in a spring. So these potential energy forces that we can solve for. External forces are non-conservative. That means it changes total mechanical energy either by increasing or decreasing it depending on what the force does. Applied force, frictional force, air resistance, tension, normal force. These are non-conservative or external forces. So the difference is internal forces, mechanical energy doesn't change. External forces, mechanical energy does change. All right, and we'll look at some examples. So here we got a ball up here. It falls from a height of 2 meters down, and there's no air resistance. So we have potential energy that's up here, and that's due to gravity, and then it comes down, it's still due to gravity. There's no air resistance. It gains speed because energy is being converted to potential to kinetic. This means it's definitely going to be conservative. So total mechanical energy is conserved because gravity is what we're talking about. Here, we got no friction, and we're gliding down and back up the hill. But we're starting at this point, ending at this point. So we lose potential energy. But that energy gets converted into kinetic energy because we have speed, right? We gain speed, but we have a velocity here. So we start from no velocity to having a velocity, and we start from this height to this height. But total mechanical energy is conserved. So again, this is just gravity doing all this. So therefore, this is going to be conservative. Baseball traveling upwards towards a man in the bleachers. So the baseball's traveling upwards. If we say there's no air resistance, then it's for sure conservative. If there is air resistance, it is non-conservative because the wind's going to push back and do some work on the ball. But if there's no wind, it's going to slow down because it's going to increase potential energy but decrease kinetic energy. But if there's work, all right, from the air, then it's going to be non-conservative. Here we got bungee cord, right? So the bungee jumper starts to fall. So we have potential energy decreasing, but kinetic energy also decreases. But then you got spring energy that's going to increase. So spring, gravity, kinetic, but the big thing is this, it's all conservative. So the mechanical energy from the beginning is going to equal mechanical energy at the end because there is no non-conservative force. Now, positive, negative work and energy change. So let's take a look at this situation. Megan drops the ball and hits an awesome forehand. So we're talking tennis. The racket is moving horizontally, and as the strings apply a horizontal force when in contact with the ball. So the ball is here. The force is applying here to hit the ball. The ball is getting energy from the applied force. When that happens, it's non-conservative because it's an applied force. Non-conservative. So mechanical energy at the beginning will not equal mechanical energy at the end. So T-ball. Player hits a ball at the T-ball. During the contact time between the bat and the ball is moving at a 10-degree angle to the horizontal, but essentially it has potential energy. When you hit it, you're applying energy. Applied force is adding energy to the system. Therefore, total mechanical energy will not be conserved. We'll actually gain energy on the right side of the equation. Okay, so mechanical energy is added, or energy is added because of the applied force. Therefore, total mechanical energy is not conserved. All right, so rusty nails is hitting a nail into a block of wood. The hammerhead is moving horizontally when it applies force to the nail. So once this happens, that nail going into that piece of wood, it's going to make friction. And a frictional force is what makes it difficult to pound a nail into a board. So that frictional force is going to be non-conservative. Therefore, it's a non-conservative situation because there's friction. When you're hitting the brakes on your car, right? Your kinetic energy is decreasing without a change in your potential energy. Where does the extra energy come from? Well, the extra energy to conserve, even though total mechanical energy isn't conserved, is friction. Friction's non-conservative. So if we see friction or resistance of any sort or applied force, again, total mechanical energy not conserved. So now when you push off the diving board or off the starting block to start a race, right? Swim race. This reaction force, all right, is going to be an applied force. This applied force means it's non-conservative. So that total mechanical energy before and after is not going to be equal. Weightlifter applies a force to lift the barbell above his head at constant speed. Now this one's kind of tricky because you're thinking, oh, we have gravity. Gravity pulls it down. The force we're applying to lift it up, okay, is going to make this non-conservative because it's going to be an applied force in this guy with the big guns, okay, lifting the weightlifter up or lifting the weight above their head.